Okay, good morning everyone. So last week we have been already start to discuss the basic for MOSFET operation. So we have been showing the case of our gate bias smaller our threshold voltage. So in the case of the gate bias smaller threshold voltage, so there will be no inversion electrons in the channel. So we don't have the inverted electrons here. So therefore we expect there's no current. And one thing is worth noting that because we have the PN junction already formed between the substrate and drain, and also the substrate and the source. So therefore we have the space charge region in between. And the space charge region between the drain to source, between the drain to substrate and source to substrate will highly determine some of the non-ideal effects. And once we start to apply the gate bias larger than our threshold voltage, so therefore the electron can be induced under the gate region. In the meantime, we apply the positive drain bias, so the inverted electron will be attracted from the left to the right. In the end, we can have the current through inside the MOSFET, and that will be our basic operation for the MOSFET. So now we have to discuss something additional, especially related to how to fully understand the typical ID-VD characteristic. So in the first case, when our gate bias is larger than our threshold voltage, and another bias is that we apply the VDS is smaller than our it's pretty small. So first we discuss the case our gate bias is larger than threshold voltage, but on the other hand we only apply a small VDS at this moment. So at this moment we expect that we can have the uniform formation of our channel inversion charge. And this is because at this moment that our VDS is very small, so we didn't expect any influence from the drain side. So at this moment, the channel will be mainly determined by the gate side as well. So will be mainly determined by the gate bias. So but we still have the smaller drain bias applied. So that means our electrons can still flow from the left to the right hand side. So that would be our electron current. In the meantime, if we look at for the ID and VDS characteristic, this is the one fixed VG. So we fixed one VG. So now we are looking for the ID versus the VDS characteristic. And right now, the current will linear proportional to our VDS because now the channel is a uniform formation. So as long as we increase our drain bias, we expect we have more and more electron can be flowed to the right hand side. So the current is linear proportional to our VDS at this moment. Furthermore, once our VDS increase, then the voltage drop across the outside near the drain terminal decrease. So if we look closely for this region, if our drain bias is increased, so that means our VGS minus VD is decreased. Right, so this is considered we have the fixed VG. So previously we also considered this is a case of a fixed VGS. So we have a constant VGS here, but now if we continue to increase our drain bias, and for sure the voltage difference between gate to drain is decreasing, as shown as can be clearly understood. And however, our carrier concentration near the drain side, our carrier concentration near the drain side is basically proportional to our bias, especially related to our drain side bias. So once our drain voltage increase, our voltage drop between the gate and drain will decrease. And on the other hand, our carrier concentration is certainly proportional to our VGS minus VD. So therefore, we can start to expect the carrier concentration will gradually decrease because of the drain bias increase. So the voltage drop across the outside near the drain terminal decreases, which means that the induced inversion charge density near the drain also decreases. So now we can have a certain expectation that the carrier density here is decreasing because of the drain bias increase. So that's why the inversion electron here will not become uniform along the channel anymore. You will see there will be slightly thinner channel near the drain side compared to the source side. And the decrease of the carrier concentration also indicate once we continue to increase our drain bias, our current will start to, the incremental current, the increase of current will start to decrease because of our carrier density near the drain side is decreased as well. So the incremental conductance of a channel and the drain decrease, which means the slope of ID versus VD curve will decrease. The slope will decrease as shown here. So that's in the case when we start to gradually increase our VDS. Now, in the further case, if we continue to increase our VDS, and actually we will start to reach the point when VDS increase to the point whether the potential drop across the R side at the drain terminal is equal to our threshold voltage. So that means the voltage drop here, which is VGS minus VD, and because we continue to increase the drain bias, and therefore there will be the certain point that our VGS minus VD will exactly equal to our threshold voltage at this moment. Now we have to recall the basic definition of threshold voltage. The basic definition for threshold voltage is the bias that we can start to induce the inversion electron in the channel. So if our gate to drain voltage drop will back to equal to our threshold voltage, that means our inversion channel, our inversion electron will be equal to 0 at this terminal. So the induced inversion charge density is 0 at the drain terminal. So at this moment, we call this VDS is what we call the VDS saturation. So that would be this VDS set here. So that's how we define at this moment the VDS is called as a VDS set. So at this moment, our N is equal to 0 at the drain terminal. Now we will be interested in to know if we further increase of our VDS and what will be the impact on our device characteristic. So the next is we are going to continue to increase our VDS. So when VDS becomes larger than VDS set value, the point in the channel at which the inversion charge is 0 move towards the source terminal. So now we can see this. Originally, we have the channel at the 0 at this point, but now we continue to increase our drain bias. We start to see the channel will move towards the source terminal. And this is because, as already said, we have the PN junction in the drain side. So if we continue to increase our drain bias, the larger drain bias actually means that we try to reverse this PN junction. And once we reverse bias this PN junction, that means our depletion region will further extend. So we will become to have the larger depletion region or space charge region. And this will lead to the move of the channel towards the source terminal. So basically, this region is mainly due to our space charge region. Because right now, we apply the high drain bias, but the high drain bias will lead to the reverse bias of the PN junction in the drain side. And if we increase the reverse bias, and then our space charge region or depletion region will increase. So this increase will push our electrons channel move towards the source terminal. So, but now the question will be, how does this electron can still flow inside the channel? So we have an electron channel, inversion electron at the channel. But once the electron start to move from source to the drain side, and once the electron reach at this moment, the electron will start to be influenced by our electric field. Because this is under reverse bias, this is inside space charge region, we have very high electric field in this region. And therefore, travel through the channel toward the drain. At the point where the charge goes to 0, the electron are injected into a space charge region where they are swept by the electric field to the drain corner. So just let me illustrate the operation here again. So once we increase our drain bias to a certain point, we start to reverse bias our PN junction in the drain side. So reverse bias of PN junction will create the larger space charge region. So therefore, our channel will start to move towards the source terminal, as shown here. Now, we still have a loss of the electrons at this channel. So the electron will still try to move from source toward the drain region. But however, once the electron reach to this point, they will be influenced by the electric field, because in the space charge region we have a high electric field. So now the electron will sweep through to this region, because due to the electrons help them to inject from this point to this point. So in the end, we still can have the electron currents inside the channel, but now our current is not continue increase, is maintained as a ideally as a flat current, because right now our carrier density didn't continue increase, but however the electrons can still be traveling from the source to the drain due to this electric field. But now the current will become flat after, as long as our VDS is larger than VD set, and this region is what we call as a saturation region. So that's why this VDS, we call this the VDS bias, make the transistor reach to a saturation region. That's why we call this as a VDS set. Okay, so that's at the one fixed VG. But now, next is we will be interested in to understand the full IDVD characteristic with a different gate bias. So previously we have already discussed the first important curve for MOSFET, which will be the IDVG. So in the case of IDVG, the curve will roughly look like in this way, and we have the threshold voltage here, and we have the drain current. This is the drain current versus the gate voltage. But usually when we characterize our IDVG, we only will fix at the one drain voltage. Especially we will be interested in the case of with a smaller drain bias. So that's a typical characterization condition for our IDVG curve. Now, on the other hand, we still have another very important plot which is related to our IDVD characteristic. And this is a characteristic with respect to the different gate bias. So this is an increase of gate bias here. So our VG increase, and then we try to understand the full IDVD curve with a different gate bias here. And first of all, once our gate bias is larger than threshold voltage, so for sure we can start to see the current will increase, just like the case we said before. But there's a turning point between the left region and the right region. Usually the left region is what we call the linear region, and the right region is what we call the saturation region. And also, not only the current is increased as the gate bias increases in the saturation region, but as well in the linear region. So sometimes people call this as a non-saturation region, but the linear region is a term more often used in the literature. That's generally we call this as a linear region. And the typical current equation showing here, the drain current is equal to our channel width times our mobility times our Cx over 2 channel lengths times our gate bias. So anyhow, our current is always related to our mobility, our oxide capacitance, and our gate bias. The similar is also in the saturation. The current is related to our mobility, oxide capacitance, and also the gate bias as well. So, as you see, the current is strongly correlated with our oxide capacitance, Cx. So the next questions we need to understand is we need to understand the basic characteristic for the oxide capacitance, especially related to the different bias and different frequency. So that's why in the every semiconductor class, there's always one chapter is talking about the MOS capacitance here. So when we talk about MOS capacitance, first we need to understand how we usually to characterize our capacitance. So usually when we try to characterize our capacitance characteristic, which we consider a bias. So this is our gate bias. First of all, we will apply a constant DC bias. So the DC characteristic has already discussed in previous slide. So we will not, it's nothing interesting for us anymore. But in the case of the capacitance characteristic, what we are trying to understand is once we have one DC constant bias, but on top of the DC, we will apply a AC signal. So in this case, that would be DC plus the AC. So this is actually something that we are interested in. We are curious about how this AC signal can influence the charge inside our MOS capacitance here. Because if we look at this period, the voltage here is equal to DC plus AC. So that means this additional voltage due to the AC could give us additional charge. That's what we usually call as a delta Q. On the other hand, this is a region where our DC minus AC. So this can create the case our charge is decreased. The total charge is equal to the original charge minus a delta Q prime here. So therefore, we will be interested in this case. Now we have to use the Venn diagram to understand. So the Venn diagram is based on the structure. We have the P-type substrate, and on top of P-type substrate, we have the dielectric, which is oxide. And on top of oxide, we have the metal. So we have a metal oxide and substrate. So this is the typical structure for the MOS capacitors. But now we are curious about the Venn diagram along this region. So this is a graph of the Venn diagram around this region as well. And then the first case, what we would like to discuss is if we apply the negative VG. So we apply a negative DC bias. And for sure, usually once we apply negative DC bias, so that's equal to this region applied the negative gate bias. So negative gate bias can start to attract the positive holes below the oxide, which can also be seen in the Venn diagram. In the Venn diagram, we can see this region of Fermi energy is close to our valence band. That suggests we have a higher hole concentration in this region. So we will have the positive charge here. But now, as I say, in the case of the MOS cap characterization, we will not only apply DC but also AC as well. So we apply the negative DC, but additionally we apply the AC. So AC will create the positive or minus some of the delta charge, which is due to this delta VG as well. And this delta VG will create a certain influence on our charge distributions inside the MOS capacitance. So now to further analyze the MOS capacitor, usually we will draw the graph similar to this one. That's basically as a charge distribution. And first of all, because we apply the VG in the metal side, so that means we have a negative charge in the metal region. And to balance this negative charge, to reach for the charge balance, for sure we will start to have the positive charge that will be generated under the dielectric. So this minus Q and positive Q just exactly to reflect the things here. We apply negative VG, so that's why we have a minus Q. And negative VG will induce a positive charge under the oxide, so that's we have the positive Q here. So I believe that's if you combine with the device schematic, that could be very easy to understand. But now the thing is, once we have the AC signal will give us a delta VG. So as I say, delta Vg will also create the delta Q. First is in the gate side because we apply DC plus AC in the gate region. So this is because of delta Vg due to our AC signal. And since we have the delta Q here, for sure, we will also induce the delta Q in the channel region as well. So now, because of this delta Q related to the frequency and AC signal, this delta Q related to the frequency and the AC signal, so that will induce the capacitance between these two charge, and that is our first case, what we usually call as a accumulation capacitance. So now, if we try to plot the capacitance versus gate voltage characteristic, the first one is we will have the, because we apply negative gate bias, so this is a region for the negative gate bias. And why we call it accumulation, because we will have the whole accumulations under the dielectric here. So this is generally we call as a accumulation. So at this moment, our accumulation capacitance will be exactly equal to our outside capacitance, right? Because this is our dielectric, so this is our outside region. So that will be exactly equal to our outside capacitance. So this is a region where silicon dioxide is. And usually how do we characterize our dielectric is by considering the, first of all, the dielectric constant, and secondly, the oxide thickness. So this is our oxide thickness. So therefore, the C accumulation capacitance is exactly equal to oxide capacitance, will be equal to exon oxide over Tx. So sometimes lots of students is easily confused about the MOS capacitance. Of course, in the beginning, if you are the first time to hear about the concept related to DC plus AC, and then you see the Venn diagram here, at first you also need to a little bit spend some of your time to understand the charge distribution. You will probably be kind of the confused for all of the analysis here. But if you take time to go through once, but the conclusion is very simple. The conclusion is our accumulation capacitance is exactly equal to our outside capacitance. I think that's a pretty easy conclusion. So again, since we finish this part, for sure the next one is what happens if we continue to increase our gate bias. So if we continue to increase the gate bias, that means we apply the Vg, and Vg is become more and more positive here. And right now we have the positive Vg here, so that means the charge here is positive. The positive for sure will lead to the generation of a negative charge in this region. But right now, our EF is still is getting close to the Fermi energy here, but in this region still mainly close to our valence band. So that means we start to form the depletion region. So now the charge distribution will be drawn as this schematic showing here. So once again, we start to apply the AC. So this is due to our AC signal. And the AC signal will reflect the delta Q here. Now this region become our extra series capacitance. So therefore, our C total capacitance is equal to Cx in series with CSD here. So now our total capacitance is equal to 1 over Cx plus 1 over CSD here. So now we can expect, if once again we plot capacitance versus voltage. So previously we have been knowing this is a accumulation. That means our CACC is equal to our Cx, but the series capacitance actually will lead to the smaller total capacitance. So that means our total capacitance is start to decreasing because of this additional series capacitance. So this is a region usually we call as a depletion region. And why we call the depletion? Because we have a depletion region forming here. So that's why we call this as a depletion region. And one thing, the reason why this is not like the constant decrease, with is a kind of like with a certain decreasing. This is because our capacitance CSD is related to our depletion width. Depletion width is here, and the depletion width is also as a function of a gate bias. So therefore CSD is not constant. Okay, so the last part, which is related to our inversion, so that will be our last part. So in the case of an inversion, we consider the bias where our VG will larger than our threshold voltage. Here in the MOSFET is actually we consider the VFB, the flat band voltage here. So if we don't know the band diagram, we just purely see the device schematic where we have the P sub, and on top of P sub we have the dielectric, and on top of dielectric we have the metal. So now we have the metal oxide and also the P substrate here. So now if we are still not get used to have the using a Venn diagram, but the conclusion is same if we using the schematic of our transistor. So right now if we apply our gate bias at this point with a positive gate bias, where our gate bias is larger than threshold voltage here. So we expect to have the inverted electrons below the channel. So the inverted electrons will be happen in this region as well. And also this can be verified in the Venn diagram, because Venn diagram also start to showing our Fermi energy close to our conduction band. So once our Fermi energy close to conduction band, that means we have a high electron density in this region. So now again, we first to consider to have the positive gate bias. So that's have the positive Q. But now, because of the positive Q for sure, it means that we will have the negative Q here. That is mainly due to the electrons, the inverted electrons here. And also because this is the process that we start from negative, a little bit positive, and then very high positive. So we still have this depletion capacitance, depletion region that we have been shown in previous slide. So now we apply the additional AC. But then the additional AC will only start to influence the inverted electron. The additional AC will be only influenced in this region, not in this region anymore. This is because right now our inversion channel density is very high. So therefore, this will reflect the additional charge will be only happen in this region, and that means our depletion region XDT here is no longer increased. The reason for no longer increase is because this additional charge, because this charge here is in the channel is increased very fast and is a high density. So however, the additional charge here will be only reflect in this region rather than this region anymore. So now again, if we look at the capacitance in the inversion region will be again equal to our oxide capacitance, because right now the capacitance characteristic reflect the charge difference between this one and this one. So that would be exactly identical to our oxide capacitance. So now we can complete the full picture for the CV. Once we have a CV characteristic, so from left we have accumulation, and as we increase the gate bias, we start to have this depletion. But because right now, in the case of inversion, the capacitance will back to our oxide capacitance. So therefore, in the region of inversion, we expect to have a same capacitance like the accumulation. So that's the inversion. So we will have this transition region. And normally, this is the case for the low frequency capacitance, because the charge inversion here can follow the frequency. So that's in the case of a low frequency. But on the other hand, with a high frequency case, our capacitance will be as low as shown here. That's in the high frequency. And this is because due to the high frequency effect, the inverted electron here cannot follow the frequency effect. So therefore, our additional charge will be reflected on here. So that's why our capacitance will back to this in series with this. That's in the case of a high frequency. So finally, we finish the basic related to the MOS capacitance. If you are not very familiar with this, I suggest you can look the Semiconductor Physics and Device, the textbook. Usually this textbook has a very detailed description of this MOS capacitance characteristic. But as being the reliability, we are not only interested in the basic CV, but actually we are also interested in how to use the CV to understand our reliability issues here. So in the case of the CV characteristic, the most important the C value for us is a flatband voltage, as shown here, and CFB is related to the voltage that's equal to the flatband voltage. So in this case, we have the CFB here, and this is an illustration of the CV characteristic based on the biasing condition. So what does it mean, the biasing? So we give this capacitance as a constant bias. And with this constant bias, we will start to see the shift of the CV curve. So now you can see there is a very obvious CV shift toward the left. So if we try to calculate our VFB flatband voltage, VFB versus our time, and we try to extrapolate each VFB as well, then basically we can have this graph where our flatband voltage, because flatband voltage is shift to right, so that means our VFB is gradually decreasing. This is a case under the bias. The biasing here is actually means this is a case under the stress here. And in this graph also shows the case of the recovery. So recovery, that means this is a condition that we don't give any bias, which is most of the case is our VG equal to 0. So that's the case we call the recovery. So in the case of recovery, you can see the shift towards the right. So that means our flatband voltage is gradually shift back. So that's why sometimes we call this as a recovery. And there's a timing can be seen in the left hand side is under the stress, and right hand side is under the recovery. And basically, if we see a negative shift of CV curve, which is most probably due to we have the certain trapping effects. And once we have a negative shift, that's most probably due to the positive charge. Of course, in the lots of cases, we will have the positive shift. So this positive shift that suggests we will have the this positive shift suggests that we actually have the trapping that can induce a negative shift, negative charge. We will have a negative charge. And more detail related to the trapping that causes the positive charge or negative charge that causes a shift in the left and right. We will talk more detail when we talk about the interface trapping and the bias temperature instability. And another thing is just want to illustrate whenever we try to analyze the CV, we always have to keep in our mind that the goal is to help us to understand the MOSFET. So definitely the CV characteristic should have the same phenomenon like we see in the typical MOSFET characteristic. So in MOSFET characteristic, we are interested in the IDVG curve. So in the flash, we have this IDVG curve where we have a VTH. And with a certain bias, we can also see the IDVG will shift to the left. That's because due to the positive charges. And also with a certain bias, we can see the shift toward the right. That's because due to the negative charges. So basically, when we try to analyze the flat band voltage in the CV, it's almost identical to the case we analyze the threshold voltage under the different stress and the bias condition. So now we need to bring more the concept related to the reliability, because so far we're still in the phase of the basic semiconductor physics device. I believe you will learn this in more detail in some other classes. But in here, I want to bring more focus on the reliability issues. So now we can start to look at what would be the reliability phenomenon that you will see in the MOSFET transistor and the typical IDVB and IDVG under the stress. The stress here, it just means as we try to bias our device with the time. That's what we call the stress. So as we already know, the typical IDVD is shown here. We have a typical IDVD characteristic. And also, we have the typical IDVG which is equal to that's a typical IDVG characteristic. So what happens if we have the transistor, especially a MOSFET? This is a typical MOSFET. If right now we this is gate, source, and drain. If right now we consider to bias VG 5 volt and we bias VD 1 volt for a certain time. For example, we consider we stress at the VG equal to 5 volt for 1000 seconds here. So normally, once we start to apply the long-term stress, the phenomenon that easily happen is related to the trapping effect. So the trapping effect means because first of all, once we apply the gate bias, as you already know, we will start to induce the electrons in the channel. So that's just because due to the positive gate bias. But the problem is we have a lot of the defects in the interface region. So we have the defects here. And this defect will cause the issue that the electrons can start to be injected and stay inside this defect region. And once these electrons are located in this defect region, that will become the issue of the trapping effect. And since we consider this is a negative, the inversion, the charge in the channel is a negative electron. So that means this trapping effect, which are the negative electron located in the defect region. So this trapping effect is mainly due to the negative charges, right? So once we consider the negative charge, so we can back to the previous slide. Once we have a negative charge, so we can foresee that every curve should be shifted to the right, because right now we have a negative charge here. So therefore, this negative charge and trapping effect can cause our threshold voltage shift. But not only the threshold voltage shift, also with the current decrease. So first, threshold voltage shift should be easily to be understood because we already, previous slide has already shown we have the IDVG curve. Our fresh curve is looking like this, but after the stress, we see the threshold voltage shift. So our IDVG become like here. So this means our VTH shift. But at the meantime, with the same VG at here, actually the drain current is decreased as well, right? Because we are the transistor is always biased with the same operation voltage here. So now our threshold voltage shift to the right. So that means this, we are applying the same gate bias. So amount of current here is decreased compared to the previous one. So generally we will foresee there will be the right hand parallel shift to the right as well. So this current decrease that can also reflect to the case of the IDVD. So in the beginning we have the IDVD like here. But right now we have a drain current decrease. So that means our curve being stressed will become like in this way. So we will have the obvious drain current decrease can be seen. And the drain current decrease also suggests our resistance increase. So this is a typical outcome if we have the electron trapping in the MOSFET that's under the case with a positive gate bias stress. So we will see our threshold voltage shift to the right, our drain current will decrease, our resistance will increase. And this, which is mainly due to we have the electron trapping in the interface. Or dielectric inside. So now this is one of the interesting summary slide try to illustrate the goal for this class as well. So first of all, we need to understand what will be the phenomena after the stress. So after the stress, we have seen the current decrease, we see the threshold voltage shift, we see the current decrease. And next is we need to start to understand what's the cause for this shift, which is because we have a negative charges. But the next question is, where are these charges happen? So now we understand this is electron trapping in the interface and dielectric. So finally, this gives us a hint. If we want to solve this reliability issue, we should focus on try to optimize the interface of gate dielectric that can induce a less trapping effect. So that's generally how we reliability people is doing. Not only first we do the testing, we analyze the phenomena, we understand the reason, and then we have to propose the strategy how to optimize the device stability. Okay, so next, just a few more slides for this introduction for the typical device operation and fabrication. And another thing I want to illustrate is this is CMOS here. So CMOS is what we call the complementary MOS here. So it's basically as a combination with a MOSFET and also combination with a P MOSFET. So the N MOSFET is basically we apply the positive gate bias. We will have the electrons, formation of electron in the channel. On the other hand, the PMOS is we apply the negative gate bias. We will have the holes formation in the channel here. And the purpose to have both NMOS and CMOS side by side together is because we want to build up the basic unit as a logic circuit which is look like in this way. So on the top, which is a PMOS. On the bottom is a NMOSFET. And we will connect the gate together and also connect the outside together as a one input, one output here. And the purpose for these NMOS and PMOS connected together is going to try to realize a inverting function, which is generally called as an inverter here. So the inverter is a function where we apply a series of the digital signal, something like this one. So in each digital signal, we can define this as a low, which will be 0, high is 1, low, high, low, high, low, high, low. So that will be the 0, 1, 0, 1, 0, 1, 0, 1 as we provide this input signal. And the output signal will be inverting. So that means as an input of 0, we have output as 1. So that will become like here. So then we will, with the CMOS, this inverter circuit, so we can have 1 0 1 0 1 0 1 0, this kind of the output. So this is the function for this CMOS. And to realize CMOS for sure, we need to have the NMOS plus PMOS. So that's why in the lots of literature, when we talk about the demonstration for the transistor for this logic application, for sure we will demonstrate the IDVG characteristic. But just not only the MOSFET. So we have a MOS here, but at the meantime, we should have the PMOS characteristic here. But the general issue to have this CMOS with N and P, the issue will be usually the mobility for the holes will be smaller than the mobility of an electron. That's in the case of silicon. But in most of material almost seems showing the similar things. The hole mobility is always lower than electron. So that's why in the advanced transistor, we are not consider only the silicon-based PMOS. We actually will consider for other material of the PMOS, try to enhance the hole mobility. Okay, so here is just a quick show like for you guys that how we usually fabricate a transistor. In here we won't go too much detail, just for your information. We first have a silicon crystal growth. We do the epitaxy, we do the ion implantation, we grow the oxide, we have the isolation oxides. We have a metal, dielectric, metallization, and plasma etching. So here is some key process state. For the first one is oxidation. So oxidation is one of the important process for silicon, because silicon has a very good thermal grown dielectric, which is a silicon dioxide. So we grow the silicon dioxide here, which we use as a dielectric. So the basic idea is that we have a piece of silicon material. We have the oxygen flow will be diffused and put them in the certain of the tube. So then you will have the very high temperature oxygen will react with our silicon in the end to formation of the silicon dioxide. And another one is, for example, this is lithography. So lithography means that we have a certain UV source, and this is a UV absorbing material, and this is a PR. And because of this, we have photo mask here, so then the UV light can only penetrate in this region, and this penetrate UV light in this region will influence this PR characteristic. So once this PR characteristic has been influenced, then we can easily remove the PR in this specific region. And regarding for the ion implantation, so it's a very often used process try to define the certain doping in certain region. So this is a case with when we do the ion implantation with one energy. So usually with one specific energy, the particle will usually have the one similar like a Gaussian distribution with a peak around region and start to decrease to the left and the right here. And in order to make sure that we have a uniform distribution of certain particle in the certain region, we will do the multiple ion implantation. So usually we will have this one. This is one implant. We have the two implant. We have the third implantation. So once we have this implantation, the total implantation concentration will be the summation of all of them, so it will be equal to like this one. The goal is because we want to have the uniform junction like here, but of course it's not possible, so that's why we can do as many as an implantation stage, try to create the junction that have the uniform concentration. Okay, so that's all. So I think this is just a quick like a wrap up for the typical CV characteristic, and the right hand side is a typical how the MOSFET operation. So you can look up by yourself for the lots of the textbook also mention the same things. So we will take a break. This is some more information for yourself. We'll take a break and come back in 10 minutes later.
测 CV 图的时候，这三个流程可以再说一下，就是你说一开始是accumulation， 然后中间是那个观察出通道，
对，
然后最后那个高频跟低频是
高频低频，高频是因为你这个高频的时候这边的 inversion chart 要跟不上，所以它最后的高频的 additional data 就会反映在 diffusion region 的尾巴，所以它还是会变成为 CX 跟这个 C 的这一段的 series 串联，对，所以它这张还变得很低。简单来说，就是你的这个 data Q 不会产生这边，就会产生在这个尾端，因为这边的 inversion 的 electron 跟不上它的频率的反应。
好，我就理解。
OK。
想问，
对
这个高频，
这个高频低频的话，你的这个 data 就可以反映在这边，会反映在这边，因为你这边的频率比较慢，所以它的这个 inversion electron 可以 follow 上。对，那高频的时候，你这个 invert 出来的 electron 它没办法 follow 上它的频率响应，所以这时候它的 charge 是会被累积，一样会累积在这边，所以这时候会等于你一样会等于C oxide 跟你的 C 的这一段的串，所以它还是会是低的。它会跟前面叠回去，跟前面。
也就是说高频就这一个就不会在这，
对，
可能就这样挡住，然后这一个就会过来，
对，
就会加在这边，然后就会直接变成这一块，
对，
就直接合并成这一块，变成。
它主要是看 C 值，主要是看你的 delta Q 反应的区间。
那这样的话，低频就代表这个长度会增加，
对
吗？
对，
就是跟高频的比会比较高，
不一定会长度，
就是跟高频的比，这个长度会比较长。
对，因为高频的话就只有这一段，对吧？低频都这样子，高频就变这样子。就是高频的时候，它基本上就跟前面这个跟这个电容是一模一样 ，CX 跟 CSD
就会有两个电容，然后低频的时候
就不会两个电。低频的时候，
因为它跟得上 AC 的响应，
对，没错。
所以
对，
这一段就会过来，
对，
就这
对
的一个我知道了，因为像这边就是这边有加，这边在这一块。我知道。这个是像高频，
对，
然后低频就会是这样，然后高频可能就会类似这个图这样。OK， 好，谢谢。
其实这个是什么？是 charge concentration。
这个是 charge distribution， 这是它的这个 charge 的分布。
所以为什么有的会有这样并法？这个高是什么意思？
高就是它这个是你的这个大小，这是空间，这个是反映在这边的空间，这个反映在这边的空间，这个反映在这边，所以你的 x 轴是你的 location， 它的 y 轴是你这个 charge 的大小。
对，这 dq 是说当它有那个
AC 的时候，它会反映你的 delta Q，
然后它就会造成说这个 OK。
对。
然后其实我不理解，这个是说，这边是说如果 negative shift， 就是说这个 get voltage 是比较 negative 的话，它这个 C max 就会变高。然后如果你 positive bias 它的话，它会越来越低。
不是，他的意思是说我们先把它给一个 bias， 它有一个负的 shift 的话，就代表说它是有 positive 的 trapping 的现象产生，才导致它有负的漂移的现象。
负的漂移现象。
对。
是说，如果你 positive 越多，那么它的 voltage shift
它就会往左边飘。
就是
对。对。
是。
这个的话，其实就讲说，你在低频的时候，你的这个 charge 在这边，它可以跟上你的这个 AC 讯号，所以你产生的这个 inversion 的 electron， 它是跟上你的讯号，所以它的 delta 就会反映在这边。对，那如果说你在高频的时候，它 delta Q 你的这个电子是跟不上高频的讯号，所以你 delta Q 不会反映这边，会反映在这边。所以这是
在那个控环区。
对，所以这边时候它就会变成跟这个的一模一样 case。CSD， 所以是 CX 跟 CSD 的串。对，所以它才会下来之后就一直平。对。
所以这边就要讲说，在 immersion 状况下，低频的话会反映在这边。
对，没错，对。
然后
高频的话，它跟不上，所以它只会反映在这边。对。
那反映在这边，意思是说，它的电子是会比较多出现在这个区域。
不会，它只是这个，因为它是 AC， 它你主要的电子还是被 DC dominate，AC 只有一点点。对，AC 只是这个 delta Q 而已。对，它的这个，因为我们 C 值的算法是要根据你 delta Q 的产生的地点，那它 delta Q 在高频的时候，它产生地点是这边跟这边，所以它的电容就会变这样子。对，但是它产生的这个 charge 还是被 DC dominate。对。
那老师这个，我听不懂这个地方。
这个地方就是说你这个 implant 的时候，简单来说就是，你一个你一个这个 junction， 就是假设你要打成一个 N part 的地方，那你就是打 implant 下来。那你打 implant 下来的话，如果你只打一道的话，它的 concentration profile 是会这样。对，所以你这个 junction 就不是 uniform。对，可是我们要想要做成 uniform，所以你就要打很多道，打第一道，然后再打一道比较强的，再打一道比较淡的，所以你这样子total就会看起来很像一个平均，因为 ideal 我们是要得到一个就是平的， 对，所以你打越密，它就越像平的。
哦。
对。
好，这样子。
就是我先问这个，就是我之前就修过其他老师的班，然后但我有点忘记为什么就这边就是他可以，就是我有点忘记这边的那个原理是什么。
它这边原理其实简单来说，就是你的这个 voltage 在这边变少，你的 channel 基本上就跟你的它实际感受到的电压它有电压有关系。对，所以你为什么一开始会 uniform？uniform 是因为你全部的电压，你 VD 很小，所以整个 channel 都只是被你的 VG dominate。对。但是所以你开始增加 VD 的时候，你这边的 VGD 就变小。VG 变小的时候，你的 channel 相对反映出来，因为 channel 的 N 就跟你的 VGD 是成正关系，对。所以
这个我听懂。
对。
我想问说，就是我知道这边因为有 oxide， 所以这边是正偏压，所以这边就会吸电子上来。
对。
所以这边正偏压不会让这边也跑电子过来吗？
会啊，所以电子会从这边吸过来。我这边有画，电子会从这边吸过来。对。
我一说它就不会累积这边变成一个变大的区块这样。
不会，因为这时候。
所以是因为这边有 oxide，所以它才会有这样的累积，也可以这样讲。
可是因为要考虑是它同时它这边还有 PN junction 的关系。
你说
这边是其实对，所以还有 PN， 它会把你的这个产生 space charge region 产生出来，所以它不会有电子一直累积在这边。对。
那我可以说，
对，
因为这算是一个 PN junction，
对。
然后假设因为这也是 P，
对，
然后这是 N，
对，
然后因为它施加正偏压，
对，越大，所以它就 reverse bias， 所以它这边也会就会变成这样，因为你的 PN 越来越大，所以这边变成一个 reverse bias。对。对。
那这样我懂。
好。
然后不好意思，我找一下。
没事，你慢慢。
因为刚刚那个我跟就是那个女同学一样，我也没有听懂。
它最主要意思其实是说就是你说 high frequency、low frequency。
不是，我是要问
那离子不止的。
对。
OK， 离子不止的简单的概念就是说，你现在有一个 junction， 这边有个 junction， 你要把它打成 N plus， 所以你要打一个 implant 进来嘛。如果你只打一道的话，其实它的这个 carry distribution 是长这样子。但是理论上我们在希望它是 uniform。所以你接下来要打很多道，你打这样子，然后再打比较深的，所以这样加起来不是就会比较像是 uniform 概念，你打越多道。
所以这横轴算是 concentration。
对，所以你打越多道，它不是这就越像一个越 uniform。对，所以类似大概这样。对。好。
笑死。
它被 voltage 就会随着它的正电上升而下降。
它正电上升是因为其实你正电上升的话，其实你会 induce 更多的。简单来说，你就可以想象，就是你这个 channel， 你有没有这个讲这种对了？你现在有个正电荷的话，它其实会让你的这个channel 会更多的负电。那更多的负电的话，它其实可以让你的这个会让你的水圈voltage数再往左边飘。这样了解？我觉得你可以想象成，先用这个 positive shift 比较好理解。positive shift 的原因就是因为你有这个 electron trapping，electron trapping 它有这个负电荷在这边的话，就会 deplete 你的其他的 electron，deplete electron 会让你的这个 inversion 的这个 channel 越更难形成，所以你要加更大的电源。对，所以 positive shift 其实就刚好是跟它相反。对，就是因为你因为你现在有一个 positive 的 trapping 那边，它自然而然就会帮你去 induce 那个 channel 的 electron，所以你变得更容易去，所以你这时候你的水圈voltage就会往左边，就不用这么高，所以就会把它全部打开。
所以说 trapping 应该就是 trapping 最主要是正电，它可以吸引更多的负电出来，所以说 voltage 就变得高。
对，所以我有个变负，因为它更容易使，因为它就是这样，就像你给个，其实简单概念就好像你给个5伏，可以 induce 这个10个电子，但是因为你现在有 positive trapping，positive trapping 就表示说好像变成你 additional bias， 所以你加5伏，它其实理论上它被感受成是7伏，所以它7伏其实感受到可以变成15电，所以你接下来其实只要 bias 3伏，就等于加原本的5伏的样子，对。
是。
流程去收。记录是多少？这个 H 是不用考虑，这个 H 是。我等一下下来看一下，对，我看一下H。你等一下下课再过来跟我讲，下课我再跟你谈。好。Just wait.
Yeah.
This is because we apply the quantum device. So band bending is mainly due to the applied device. Because we apply the device here, so then you start to see the band bending not only direct sense but also in dielectric swing. So in dielectric you will also see the band bending as well. Yes.
Excuse me,
Yes.
Professor, I would like to ask about where is your lab room in the engineer building 4, because the last week when I come to the lab room in the MRIC, Tian-Li 学长, he said that my lab room is in the first year will be located in the engineer 4 lab room, not in the MRIC lab room, right? So I would like to know because I want to make some setup for my desk.
Tomorrow
we will have
meeting.
the
Yeah,
meeting.
meeting. I will discuss with because we already have some members lab because right now for the below attributing for 411 is I would say it's almost 90% full. Yeah, but we will have some. Recently we have one member lab. Yes. So then tomorrow I will talk to the lab manager and then arrange a thing. Okay. Okay, so now we'll move to the new chapter, which is related to the defects, contaminations, and the yields. So we are getting more and more focused on the reliability issues. And generally, when we talk about reliability, most of the reliability are almost related to all kinds of defect or contaminations during the process. And of course, reliability also in the end will influence the yield as well. So first of all, we need to understand in our material side, what kind of the imperfections that could probably happen in our materials. So we have the several classification here, and generally the more important ones are the first one, electronic charge here. So the electronic charge, that for example, the electron and holes. So these are some imperfections could be happen in our semiconductor material. Or we can have the chemical impurity, we have the point lattice defect, or we can have one-dimensional, two-dimensional defect, even for three-dimensional defects. So basically, all these imperfections could be happen in our semiconductor material. In the end, that will cause us reliability issues. So the first one we'll talk about is a point defect. So basically, the point defect is the vacancy or the absence of an alternate at the lattice side. And this is the most basic defects here. So if now we draw the schematic of one crystal plane. So the crystal plane basically is a series arrangement of all the alternates. But we will find that in some of our material, there will be the missing alternates in the one place. For example, like here, it's a missing alternate in one place. So this is a defect we call as a vacancy. And also on the other hand, it could be these missing alternates located in this region, and this is what we call the interstitial impurity. Interstitial impurity. So that's the definition for this kind of the defect. Or sometimes original we have the alternates here, but now it's substitutional by the other impurity. So this is what we call the substitutional impurity. Substitutional impurity. So basically we have three kinds of defect as shown here. The first one is a vacancy, and second one is interstitial impurity, and third one is a substitutional impurity here. And our concentration for the vacancy can be expressed as an exponential minus EF over KT. So the EF is the energy required to form a vacancy here. So here is some more detailed definition. So we'll consider the intrinsic point defect. We have this one called the vacancy. We have this one called the self-interstitial. And also we have the extrinsic point defect, and this one is called the substitutional. And also the right is interstitial. So this is just a definition for this defect type. So when we talk about the point defect, at initially uncharged vacancy is we denote as a V0. So that's an uncharged vacancy. In silicon lattice can act as an acceptor by acquiring an electron, so that it becomes the negative charge, where we denote as V minus. So similarly, it can also acquire positive charge by combining with a hole and become V plus. One can also envision neutral vacancy acquiring more than a single net charge, so that we can also have the vacancy that can both have the V2 minus, V3 minus, V2 plus, and V3 plus. So that's the charge. For example, V2 minus, that means that we have the charge with the vacancy that can have the two negative charge, and V2 plus, that's the vacancy that acquires the two positive charges. So these all possibly can exist. And the next one is another well-known defect extend along a line. Along a line of the atoms in the crystal, and these bonds are generally viewed as an acceptor. That the capture electron to lower the overall energy. But now a hole can be trapped and in the recombination. So in this case, recombination can also occur. And then the captured electrons can be removed. So what does this mean? This means that if we have for example, in a lattice, there's one place can be possible to capture electrons. So initially, the electron will be captured in this region, but later on, we have another holes will flow into this electron region. So the electron and hole will be recombined. So that's what we call as a recombination. And then the vacancy will come out again. So that's become the very challenging for semiconductor engineer, because when we try to do our engineering job, we want to have very clearly prediction for the device characteristic. But these defects, this vacancy, because sometimes electron trapping, sometimes hole come in to recombine, that's become our material will be very unstable, and therefore we cannot predict the characteristic precisely. So usually we will do our best, try to limit this defect as possible as we can. So the original high electron energy state is restored, and then the process can repeat. This is the reason that the dislocation, so in this case we consider as a dislocation, are viewed as a carrier generation. And recombination center. So for example, what would be this impact for our IDVG curve? If we have, this is a dislocation, is this slide talk about a type of defect that we call dislocation. A dislocation is a kind of the defect along the line here. So it is extending a line. So basically it's a defect extending through become as a line defect here. So once we have this phenomenon, usually this will influence as well in the end our current versus the voltage characteristic. So initially we have this characteristic, and once we have the electrons trapping, so for sure that means we have the electron, once we have electron trapping, we have the characteristic shift to the right. But after a certain moment, we have the hole and electron recombination. So then we'll start to see the curve shift to the left again. So once we have a certain defect, for example, the line, the dislocation, so then this process will continuously happen between 1 and 2. So will be repeat over again. So now that becomes difficult for us, because we are very difficult to predict for the characteristic prediction. So as long as we have a difficult prediction, that also means this material or this device has a certain instability. So another concept I want to bring you guys is about the yield. So yield is generally defined as a ratio of the number of a good product produced to the total number of units stored in any manufacturing operation. So the bottom graph is showing us the yield and also the defect density progress in the past certain period. And the conclusion is, once we reduce the defect density, we can always, this is the defect density, we can always see the yield can be improved. So that's why one of the motivation to understand defect, to try to remove defect, is in the end we want to improve the yield. But once we talk about yield, we also have to understand in the practical semiconductor manufacturing, how do we estimate the yield? So generally, the yield can definitely cannot be possible to reach 100%. So the yield is always less than 100% because of following reasons. The first one is a critical design problem. And then the second one is process defects. And the last one is random point defects. Random point defect. So for any IC manufacturing steps, the overall or the cumulative yield is a product of all these wafer process yield times wafer testing yield times the module testing yield. So in the end, our yield is equal to the combination of all three. When we consider yield, as you know, yield is trying to estimate some of the good product from the huge amount of the manufacturing product. So therefore, definitely we need to start to apply the statistical basis. So in here we will talk about the first one is a binomial distribution. So binomial distribution is basically something that we have already learned in the high school. Can be physically described by the toasting of cones that have the two outcomes. One is the heads, another one is tails. So right, if you toast a cone, there will be only the two possible possibilities. One is the positive side, which is the head. One is the opposite side, which is the tails. So if a probability of getting a head in the one trial toast is P, and the probability of getting a tail is a Q. And for sure, P plus Q is equal to 1 because there will be only the two scenarios if we toss a cone, either positive side or opposite side. So in overall, the overall possibility for positive side and the opposite side definitely is equal to 1. So this is in the case that the cone is unbiased, so we don't do any trick for this cone. So that's in the end, P and Q will be equal to 50%. So that's a 1.5, 1/2 here. And in the end, if we extend, this is only the one trial, but we will be curious for the n trial. So n trial means we'll toss n times. So if we toss n times, then the probability of obtaining at least one head or at least one tail is unique, which can be generally shown in this equation. And if you, of course, in here we don't do the detail of how these distribution functions coming from. We will just show the conclusion and show the example how we use this statistic distribution function. So now we are going to show the general equation for the binomial distribution. So the general equation is shown here. P plus Qn is equal to sigma of K equal to 1 and up to the n. So now the equation will be look like in this way. So this is a general form for every case, no matter for how many toes. So, but in reality, we don't really need to use this general form. We will simplify this as a case that we are interested in. So, and also we extended to the result to the n coins. If we extending result to the n coins, each flip once and one coin flip n times, then the probability that n heads will be obtained in the n tosses is shown in the following. Of course, the equation is very complicated, so let's just use one simple example. So if we have the 3 coins and each coins will only toss once, so what is the probability of getting exactly of 2 heads here? So if we have the 3 coins, that actually only will have the 8 outcome, right? 3 coins actually will give us 8 outcome as shown here. Either 3 head, 2 head, 1 toes, or 3 toes, or 2 toes, 1 head. In anyhow, just a combination of all these head and nail in the 3 coins. And then in the end, the 2 heads will be only happen here. So this is 2 heads. This is 2 heads. This is 2 heads. So probability for 2 heads with 3 coins is equal to 3/8. So answer this for sure, because we only have 3 coins, so we can definitely calculate by our hands without any further complicated equation. But the equation can also help us to be in more complicated case. So in our case here, n is equal to 3. Capital N is equal to 3. Small n is equal to 2. And P is equal to 1/2. So therefore, the probability here, P So that's just a very simple mathematical verification, like we can easily just put out all the scenario and count what would be the case with the two heads, or we just use this equation, we can get the exactly same conclusions. So now we will also start to apply certain approximation to this binomial distribution. So the one we will use is a Poisson approximation. So in the case of Poisson approximation, where P so that's a result based on we apply the Poisson approximation. So now you might curious that what does this all related to our yield? So suppose now the number of events is equal to the number of defects here occur randomly in non-overlapping domains, and these events are independent events. These events are independent events. So therefore, the probability of a chip containing the n defect is then given by this equation. This is 1 here. So the probability of a chip containing 0 defects can be quantitatively defined as shown here, P0, which is equal to this one, and equal to y is equal to exponential minus alpha. So in the end, once we apply the purpose to apply the binomial distribution, because in the case with the yield, it's either also the two scenario, one is functional, one is value. So that's certainly similar to our case with a binomial distribution. And also yield is related to defect, so we can consider the events either whether has a defect or we don't have the defect. So that's why we can use the binomial distributions here. So then the conclusion is very simple. Our yield is only equal to exponential minus alpha. If the defect density of number defect per unit area we define as a D, then the alpha is equal to dA. So then our equation finally become y is equal to exponential minus dA. So this important equation express the probability of a chip having no defect provided. So that's consider the yield with no defect, the probability of a chip having no defect. So that's a conclusion. So now if we consider we have a wafer with n dies, so now we have to spend a little bit effort to explain what the dies mean here. We have the wafer look like in this way. This is a piece of the wafer, but usually we would not fabricate only one device in one wafer. We will try to divide the wafer in a small piece of area. So in this case, that will be this small piece is what we call the die here. So usually we will try our best to have as many as a die in the one wafer. So now we consider a wafer with n dies, and they are n defects randomly distributed in the wafer. So the probability of the given die having k defects can be also provided by this simple Poisson equation distribution, which is shown in here. Pk here is equal to exponential minus n and k here. So therefore, the probability of a die having zero defect, when we consider zero defect, because we define the good die as a die has a zero defect, can be considered the following equation, but now we put the k equal to 0, where k is a defect. So now, because we want to have the die that have the zero defect, so now we put the k equal to 0. So now this equation is become here again. So that's already the same that where we described before. It's equal to exponential minus n. That's equal to here. So again, if we define chip density D0 to be a number of defects per die per unit area, then we come up with this equation. So that's just another way to derive how we get this yield equation. So the yield, if we try to understand this equation, so we found out that yield is correlated with our area and also correlate with our defect density. So if you forget all of the calculation from the binomial distribution or from the Poisson distribution, it is fine because yield is correlated with the area. That's pretty straightforward, right? Because you have a large size of wafer, for sure your yield is always poor. And yield is also correlated with the defect density. So if your defect density is higher, your yield is always lower. So now, this is our area. This is our defect density. So now you can see the conclusion equation is relatively simple, can be easily understood, because as our area increase, our defect density increase, our yield is low. For anyone who is in this room who has a chance to fabricate the chip, to make your own chip, no matter in your clean room or university clean room or a company clean room, you all know the most difficult part to have the yield is first we need to make sure the defect density should be lower as possible as we can. And also another challenge is once we move to the big wafer, then the yield is always the issues. So now we have very solid proof for this concern based on this equation. So the strong exponential, and another thing is that if we look at the yield related to the area and the defect density has a strong exponential decrease. So that means why our yield is equal to exponential minus defect density times the area. So this is strong exponential decrease. So if we original have the die size 1 centimeter square, now increase to 1.5 centimeter square, and the yield will be changed from exponential minus d to exponential minus 1.5d. So that will be the huge drop, because this is an exponential decrease. So sometimes we also need to consider a little bit more, because previously we only considered the defect as a constant defect distribution, but sometimes the defect density is just not a constant function. It's a function with all kinds of possibility. So we might have the exponential distribution of defect, we might have the Gaussian distribution of defect. We not only can have the constant distribution defect, we can have all kinds of distribution of defect. So now we have to extend the previous consideration with defect D now is equal to FD. So again, our Y will be equal to 0. This now we are consider integration of our defect distribution function, exponential minus dA d here. So now this integral is proposed by Murphy. It's become a very important equation for the yield model. Once in the future you work in the real company, you have to deal with the yield issue, you definitely will use this equation again. You will need this knowledge again. So now let's look at the case by case. So if we consider the yield function is a constant d, so yield function constant d means that in the case of where d is constant, that means fd, this function will be equal to 0 in this region, but only equal to the, at this point we have the defect here. So therefore the function will behave like the delta function. So this is delta function. So now the y is equal to exponential minus d 0a. So that's back to our previous case. If we only have the constant d in a certain location. Of course, there are some more details that's very complicated. For example, if we consider the defect distribution is a triangular here, then we can have the results as shown here. Or we can have the exponential here. So the result is shown here. And there's some more complicated, which is this one and this one. So that will be depends on the different defect distribution function. So now if we look at for some of the real life experience of the yield, so the yield generally declines in the die located at the edge. So this is the device distance from the center to the edge. So this is edge. This is to the edge, so we can see the yield is getting lower in the edge. And also, as the number of process state for given product increase, yield also expected to drop. So that means once you have a more process, you have a one process move to the 10 process state, move to the 100 process state. So we expect the yield will drop as long as our process state is increased. So the yield projection using equation, this one is not optimistic because the defect prefer congregate at one certain location. So that means actually the defect, ideally we hope the defect is randomly distributed, but unfortunately the defect will prefer to locate in the one specific location and very close with each other. So that's what we usually call as the cluster, rather than the distribution randomly. So that's why usually our yield projection is a little bit optimistic, because in the yield projection we consider the distribution randomly, but in reality defect would be more preferred to be close with each other at one specific location. So now we have to start to move to talk about the correlation between the yield and reliability. So in the yield modeling literature, there's a concept what we call the critical area. So the critical area is how we define as AY, arise as a mathematical quantity that describes the probability that the defect will result in yield loss due to the, for example, open or short here. So for example, this is interconnection line. So this is our two interconnection line. And if suddenly we found a defect is located in here, this actually will not cause a yield. That's only cause a reliability. The reliability here is resistance increase. But if once our defect is located in this region, we will cause a yield issue, because this defect almost completely open the interconnection line. So your current cannot flow to here anymore. And this defect is also completely open the interconnection line. So this is a slightly difference between the concept of the yield and reliability. So therefore, we can write Y is equal to Y0 exponential minus DAY. So now the area is replaced as AY, because this is a critical area that will cause the yield. Similarly, we can also define a term called the reliability critical area. Reliability critical area, that's what we call the AR here. reliability critical area. That's what we call the AR. So similarly, we can also make the equation which is related to reliability R0 exponential minus DAR. So now you have to a little bit distinguish the definition between AY and AR. AY is an area that will cause a yield issue. For example, in this case, the area will cause the yield issue is just this one. As long as the defect is larger beyond this area, that will cause a yield issue. But reliability is actually, you have a defect here, but in the end your interconnection line is still functional. So it will only cause a reliability issue, but not the yield issues here. So then we can correlate this equation and define as this one. There will be a certain correlation between AR and AY, because AY is here, AR is here, so you can guess there must be a certain correlation. In here we just call as a K as a constant, and therefore R is equal to YK. So this still related to, not this so far is not really like the very complicated mathematical question, and also we won't have this question for this one during the exam. I just want to mention this is more like the information to let you guys to know, because of once in the future you are working in the real industry, you will start to face the same. But at that moment, nobody explains these things in detail. They just quickly say there's an equation showing the y is equal to exponential minus dA. People use this for yield modeling, and they just call there's a term called the AY or AR here. So this so far probably is, I believe this is pretty new for everyone. I believe normally you won't learn this in any other courses. This calculation sometimes really complicated, but the conclusion is simple. But the point here is not like that you have to know how to calculate. The point is that you have to know there's a concept related to these things, because in the future, once you meet this, you're being asked to deal with the yield issue, you will need to face this equation again. And usually, this equation sometimes there's no very systematic summary. This equation cannot be easily found in the one textbook, just not like the MOSFET. In the MOSFET, you can find in the lots of textbooks talk about the CV, how to operating, how to IDVD, IDVG. But this information sometimes it'll be randomly distributed in all kind of literature. But so in this information is mainly to have you to know this will be the still people is working on this equation to analyze the yield and reliability. Okay, so let's look at some of the example here. So people will try to correlate the reliability with the yield. So now you can see this graph. This is the yield for reliability versus the yield. So an experimental test was made of this relation by visually counting both account defect in collecting the process wafer in this one, and the number of defects plotting versus the yield defect in the log scale. So yield, which come out with K equal to 0.3. So in the end, we have the reliability is equal to yield 0.3. Something like this one. So this, in the end, for the practical consideration, is very useful, because we can start to estimate what's the defect area can both impact on reliability, or what kind of defect area will both impact on the yield. So now we will give some more additional example here. So for example, this is a case to determine the AR. If you try to calculate the reliability critical area AR, but first we need to calculate the AY. And by using the following definition, we can start to estimate. So the AY can be calculated with this one, and where PY is a probability that defect of the size X will cause a yield defect, and dx is a defect density function. That's what we already talked about. So we can also consider this graph as a one example to understand the difference between the yield defect and reliability defect. So in general, if you have the one interconnection line here, so now if you have the defects here and compare to the another interconnection line here, but now you have the defects here. So now we can see the first one is generally we consider only as a reliability defect. Because the current can still flow, although the resistance becomes higher, because the region that current can flow is decreased. But still the interconnection line is still functional. But on the other hand, this is become the yield defect. And because right now, this interconnection line cannot work as a proper line that have the current flow anymore, because the defect is completely occupy this interconnection line. So now we got the yield issues. So considering pattern of a parallel metal strip as shown in this one. So this is a pattern. We have a metal strip here. And then we have a different kind of defect here. A yield defect is considered as a complete open. And reliability defect is near open, but the particle is reduced the cross section. The particle is reduced some of the region, but the current can still flow. So that's a reliability defect. And in this literature, in here I won't talk too much detail, just because as I say, the point for this information is not actually to do the real calculation. Basically, all this calculation can be replaced by the software already. But since this you know, at least you have to know the concept here. And people have already tried to distinguish the different kind of defect. Some defect cause the yield, some defect will cause the reliability. So this is one of the results from this literature to understand what will be the different particle size influence on the, this is PR, is a probability. PR, probability of defect size will cause a reliability defect. And PY is a probability will cause a yield defect. So they try to calculate PR and PY with considering the different particle size here. So in here is consider the reliability defect assumed when the cross-section and cross-sectional area is reduced below W/4. And therefore, this is one of the examples we can go through. In figure 3, the inverse proposed law. Power law defect distribution as shown. This graph depicts the situation for the infinite metal mass with equal metal with a space of this one and arbitrary definition of reliability defect with this term. So reliability defect can occur when this one and yield defect occur when this one. So that's some of the conclusion. So as I say, here they define this size of a W over 4 is a critical dimension that will start to cause a reliability defect. Okay, so this just for you guys information. The last is that this is a graphic way to conclude this chapter, to consider the connection between the yield and reliability through the common concern of the defect, So the yield is mainly related to, for example, processing, materials, design. That's all cause the yield issue. And reliability is related to our stress, value, and the time here. But overall, the defect will both influence for our yield and also will influence our reliability as well. Okay, so here's some more information. If you are interested, you can look at this YouTube to understand the difference between yield and there's some very basic explanation for the binomial distribution. So in here, we just borrow the binomial distribution. Basically, binomial distribution in Mandarin just what we call the 这个二分法，所以一个硬币只有正面跟反面。So we basically follow this binomial distribution to use as a yield modeling as well. Okay, so I think we will stop at here and we will see each other next week.